Yeah, so I hope everyone is doing extremely well. Um, I made quite a bit of modifications to I taught this class in the droplet program, or not droplet, splash, the one that's only one day. Um, so I actually have pre-recorded videos here of the last one. So if you want to take a screenshot or something, you just access this YouTube channel and you'll see pre-recorded lectures of lecture notes very similar to this. So I made it accessible for everybody, even up to an 8th grade level. There will be maybe one or two things that I will allude to the people who've taken high school physics. I'll say, okay, like if you've taken high school physics, this is what you pay attention to. But essentially, these concepts, unless you've taken like AP Physics B, the physics concepts should be new, but the mathematical concepts, I think you'll be all right. But we will review anyway. So most of this.
Sorry, I just like to mention that I think for most of us, it'd be called Physics 1 and 2 now, not Physics B. So that's, if anybody's confused on that, just they call it Physics 1 and 2 now.
Okay, yeah, I've been out of the high school for a while. Yeah, probably Physics 1 then. It's not like the calculus, this algebra based one. So pretty much everything that we'll be talking from here actually stems from Einstein's theory. He came up with special relativity, which is what we'll be talking to in the first maybe like 15-20 minutes, and then pretty much everything he revolutionized our way of thinking about gravity, which builds on special theory of relativity, which I will talk about that now. So we'll be talking about that the majority of the rest of the class. Okay, so what's special relativity? Well, I'll give you an example of some effect that happens in our universe that was, you'll see what's very special about this relativity. So effect that happens in our universe that Einstein originally conjectured is, so this should be 21 and this should be 71. Okay, let's just say you're 10 years old and you have a twin that's also 10 years old. This twin takes off on a spaceship going about 18 million miles per hour. And he travels at 18 million miles per hour. But then when your twin comes back 50 years later, so you're at Earth, you're 10 when your twin left. So 50 years, you'll be 60. However, when your twin comes back from traveling constantly at this 18 million miles per hour, you'll find that your twin is only 40 years old. So some intuition for why does this happen? Does anyone does anyone know the answer, or does anyone have something, a word that they could say? Maybe two, 3 words. It's because time moves. Yes, exactly. Exactly. Time moves slower than you move. So how can we see this? Well, we could see this by saying that. Right now we're in 3 spatial dimensions. Like we see our universe is 3-dimensional. I could move my fist front and backwards, side to side, up and down. But if we consider our universe to have 4 dimensions, the fact that time moves slower when you're moving becomes more clear. Because the universe is 4-dimensional. So as I described, plus time. So let's take, let's just pick 2 dimensions out of our 4 dimensions. So let's just say north and east. So let's say there's 2 gyms and then they both move 5 miles. Okay. Gym 1 moves 5 miles. So let's just say they move like 5 miles in 1 hour. So they both walk for an hour. They move 5 miles. So after 1 hour, gym 1 will be 5 miles north. And then gym 2 moves 5 miles northeast. So in reality, we see that gym 2 will be actually maybe only 3 miles north, and 4 miles east. So when they come together, they both moved 5 miles, but then one twin moved more north than the other. So now let's say that time is a direction. So let's pick like time, and then we could just pick space in general, but let's just pick the east direction. So gym 1 and gym 2 both move 5 miles in this space time, this 4-dimensional space time. But gym 1 or not 5 miles. This is let's say they're moving like really fast. Like this effect has to be extremely fast. So maybe like close to the speed of light. So yeah, about 18 million miles per hour. So let's just say gym 2 moves about 18 million miles per hour in the east, or like in the east direction. Gym 2 keeps moving in the east direction. But gym 1 does not move in the east direction. He doesn't move at all. He just goes through time. And gym 2 only moves in the east direction. So gym 2 is traveling 18 million miles per hour in the east direction. And then gym 1 just moves through time. So gym 1 moves the equivalent of 50 years through time. And then gym 2 moves, since he's moving in space, gym 2 moves only 30 years through time. And this diagram is a little inaccurate, which we'll see soon. Any questions? This is a kind of conceptually. And space is representative of all directions. Yes, exactly. So at first I said space. So this is representative of all the dimensions, but if we just restrict travel to, so really this is inaccurate. I can't model all 3 dimensions with one line. So let's just say gym 2 moves in the east. So now this is only in the east direction. Cool. And this happens at low speed. So even when you're in a car, you're actually you're moving less through time as your friend at home, but it's just very low. Like you can't really measure it. It's only when you get to like insane speeds, like half the speed of light or something, where you can measure it. Okay, so let's see. Like I'm just gonna like go through a little bit of a review for like mathematics to get like a better idea of why this happens. So I think everyone, especially in 8th grade, I think you guys had Pythagorean Theorem. So there's a squared plus b squared equals c squared. So for example, if home is only 3 kind of units east, and then school is let's say 3 blocks east, and then school is 5 blocks north, 1, 2, 3, 4, or 4 blocks north, actually 4 blocks north. Then you could either walk 7 blocks going this way to get to school, or you could maybe cut through some yards if you walk at a straight angle, hopefully not houses, and then you actually walk 5 blocks. So the shortest path, let's just say there's no houses in between here, you could actually just walk 5 blocks to school if you just cut across, if you don't walk directly north, east, and north. Whereas if you just walk 3 miles east or 3 blocks north, 3 blocks east, 4 blocks north, you'll get to school the same. Okay, so I'm just going to introduce this called some notation, just because this is what you'll see if you decide to study physics more. Instead of saying the east, we call like the east-west direction x. So we say change in x. So the change in x, so delta just means change. So the change in x is 3 blocks. The change in the north direction, north-south, is the change in y, so delta y. So I'm just writing this a squared plus b squared equals c squared as the change in the x squared plus the change in the y squared equals this total change of distance. So we call it a ds. Is this clear to everybody? Do you want me to stop, keep going? Okay, so this is how we would describe geometry in our world if we lived in 2 dimensions. But we do not live on paper, on a 2-dimensional sheet of paper. We live in 3 dimensions. So there's an easy modification to that. We just add a Pythagorean theorem in 3 dimensions. You just add the change in the east-west, the change in the north-south, and a change in the up down. So just to give you a picture, if you want to know the distance between you and your friend on a hill, you would find out, okay, how far is my friend in the east direction to me? How far east is he? How far maybe north? And then how far up and down. So this total distance is just the square of this distance is just dx squared plus dy squared plus dz squared squared. And then in order to find just the distance, the square root of this. Okay, cool. So how would you, now since we know that Einstein said, and this theory was actually tested. So I should mention, that's an important point. This twin paradox was tested. It was experimentally verified, maybe in the 60s. They actually took a clock and they ran it around the Earth really fast. And they did that for a long enough time so that there should be a time difference in the clocks. So they kept one clock on Earth. They put one clock on a moving aircraft. And then when they came back, the clocks differed by the exact amount predicted by this theory. So, and I mean, we see these in other aspects too, like with particle physics, that these particles are going really fast. So there's a lot of experimental evidence for this. Okay, so now that there is experimental evidence to model the world as 4 dimensions, what should this, we call it, I'm just going to call it geometry, this geometry, this piece of geometry, what should that look like? So it went from 2 dimensions. If we live in our 2-dimensional world, the Pythagorean theorem could be here. In our 3-dimensional world, the Pythagorean theorem is east-west, north-south, up-down. So what would the Pythagorean theorem be? What would you guys say? One of you, what would the Pythagorean look like in our 4-dimensional world? And someone, or maybe you guys could just open the speed squared. Okay, cool. So remember, time is the fourth dimension. So time squared. So you think, but wait, so you think this should be correct? If you guys agree, maybe thumbs up, thumbs down. Yeah, time difference squared. Cool. That's what we think. But actually, what the Pythagorean theorem of our 4-dimensional universe looks like is this. It actually comes, the time dimension comes with a minus sign. And the c is just the speed of light. And the speed of light is definitely not 6.7 miles per hour. It is 6.7 times 10 to the 8 miles per hour. So yeah, that's bizarre, but we'll see why we need to have this minus sign, and we'll see its consequences. But yeah, let me just, for those of you who really haven't taken any physics, let me just describe why we need a speed there. So essentially, if this is miles, if we're measuring all these things in miles, and then time, we just say it's seconds or maybe even hours. We can just keep it real, keep it in the real world. So then we need some speed. So the speed of light is measured in miles per hour. So when we have c times delta t, we have some miles, some number, miles per hour over hour, and we get back miles. The speed of light is chosen for a very particular reason. This is probably one of the strangest effects that really governs all kind of the weird things we're going to be talking to you about. And that is just a simple fact that the speed of light, or light, moves at the same speed for everybody. Okay, that seems like a pretty simple statement, but let me just explain the consequence of it. So before, let me just give you a scenario where there's someone's driving a truck and there's 2 people playing catch on the back of the truck, and there's someone sitting on the grass watching the truck moving and the people playing catch. So the truck is moving at 20 miles per hour, 20 mph. The ball is thrown at, again, 20 mph. I think I meant to put 10 mph just because it'll be easier to fix it now. So 10 mph, the ball is starting at 10 miles per hour. And then, so this guy sitting on the grass would see the ball move at 30 miles per hour because the girl in the truck, she sees the ball moving at 10 miles per hour just because she's moving with the car. So she doesn't feel the car moving at the same speed. You can only really feel when you accelerate, you could feel your motion, but then if you're moving at the same speed, you can't really tell. It's like being in a train that moves at the same speed. Like if the windows are blocked off, like would you really be able to tell you're in a car? So, or in a train. So yeah, someone is connected to the Doppler effect. Yes, there's a Doppler effect. But still, so yes, there's a Doppler effect for wave, but the Doppler effect for light manifests itself a little differently because so Doppler effect for speed or for air, like the waves would change speed. With the Doppler effect for light, there is since light has to move at the same speed, just the frequency changes. So how fast the light oscillates. So maybe if light's coming at you and you're moving away from it, let's say it's blue light, instead of the light changing speed, as you'll see, the light can't change speed. So what happens is it becomes more red. So you'll see like maybe red light. Yeah, but thank you for the comment. That's important. So just to get some intuition again about why the speed of light moving the same for everyone's kind of weird, is now let's replace this this ball with a light beam, and the car is still driving at 20 miles per hour, and there's a person sitting on the grass. Well, the girl in the truck is going to see this beam of light move at the speed c, and the guy at the truck is going to move, or the guy on the grass is going to see this part of light moving at speed. So according to our relativity before Einstein, this is like not special relativity, but Galilean relativity. Galilean relativity says like, okay, relative to this guy, the ball is moving at 30 miles per hour. Relative to her, the ball is moving at 10 miles per hour. But then what's special about special relativity is that according to him, this beam of light is moving at c, the speed of light, and then according to her, this beam of light is moving at the speed of light. So this equation doesn't really violate some math. You can't add 20 miles per hour and then still get the same thing back. Yeah, any questions about this? I think this is a pretty fundamental concept. This will be the bedrock of what we'll be doing. So in order for some math to work out, that the speed of light is the same, that's why we need this minus sign. That's why we're using c as the speed of light. So let me just, let's do like a calculation, honestly. This is probably how much time, okay. This will be pretty quick. I'm just gonna, I think I meant to delete this. Sorry, this was, I was expecting it to be 12 o'clock Chicago time. But so let me just walk you through this on how we could see this time dilation. So the first thing we can do is we could just, in fact, yeah, let me just I have everything right now. I'm not gonna, why go through this? Okay, so we have this line element. Here, let me just. So we have this geometry given by this right here. And what we're gonna do, oh, there's people in the waiting room. I'm at both of them. So what happens is that we will, so we start with this, and then the rules of algebra say we could divide, if we divide one side by something, we have to divide the other side. If we divide the right-hand side by something, we have to divide the left-hand side by something. So we're just gonna divide the right and left-hand side by c delta t squared. And then if we measure the change in x over the change in t, so this is, I'll be really quick. If you guys don't follow this, please don't worry about it. You could look at the recording. This is just some technical things. So just the change in x over the change in time. This is, if I change my distance in the east direction by 5 miles in 1 hour, then that means I went 5 miles per hour in the east direction. So that's my velocity. It'll be recorded. Don't worry, I see the recording thing. And then, so this would just be the velocity in the x direction, the velocity in the y direction over c squared, the velocity. So this would be velocity in the x, velocity in the y, the velocity in the z direction, and then these two cancel out, so that'll be 1. Okay, so then we could combine these. We can combine these into a common denominator. Since they all have a common denominator, so we can combine these two things. And then just like how with Pythagorean theorem in 3 dimensions, we could just say that the space in the x squared, the displacement in the x squared, the displacement in the y direction squared, and the displacement in the z direction squared equals the total displacement squared. The velocity in the x squared, the velocity plus the velocity in the y squared, plus the velocity in the z squared. This whole thing just equals the total velocity squared over c squared minus 1. So let's rewrite our equation. We have 1 over c. Let me just write it like this. Delta s squared, 1 over c squared over delta t is v squared, c squared minus 1. And we see that delta s is just distance. C is distance over time. That's a speed, so it's distance over time. So 2 distances cancel out, and then that just equals some time. So this represents some time. We could call it tau, where tau is described, instead of t, we just call it tau. This is the new time. And we could say that that is just minus. So going back to this line element, we see that time comes in a minus sign. So that's just minus d tau squared c times c squared, and then that's ds squared. So that d tau squared equals ds squared over c squared. And then we just make this replacement. This is d tau squared dt squared equals minus c squared v squared over c squared. So all I did was I just substituted this delta s squared over c squared into here. I just call it minus delta tau squared. And then by multiplying both sides by minus dt squared, what's this? Okay, I get delta tau equals delta t squared, delta tau squared. And I'll explain what this tau means. So essentially, this delta t is a time of the observer at rest, or so of your time, let's just say time of twin at rest. Twin at rest. This is the velocity, your velocity, and this is your time. So now we have, so using this, we have an equation that from right away, we see that your time will be different from the time of someone else at rest. So the time of your twin at rest will have a different time than you, and the difference is calculated by this equation. Tau is a Greek alphabet. Yeah, that is. So a lot of times in physics and in science, you'll see just things coming up from the Greek alphabet, things popping up. Okay, so let's just, so we have an example problem. Maybe we could all work this out. So I'm a Frozen fan. When Elsa let it go, I was very inspired. So I'm in the line for the 3rd Frozen movie. oops, let me just take this. And I'm actually waiting 10 hours because I want to be like the first one to see it. So in order to be the first person to see it, I have to wait 10 hours. So how long will my twin jealously watch me wait in line if he is moving 1/2 the speed of light? So this is actually, in this situation, this will be my time. Delta T would be my time. This would be my speed, or my twin speed. And this will be my twin's time. Okay, so let's go through this together. My time, it's 10 hours, so 10 hours squared minus my speed is 1/2 c. So I have 1/2 c squared. I promise this is the only math we're going to be doing this whole time. So please do not, if you are not following this this very quick procedure, please do not worry at all. Everything else will be totally conceptual. So could someone, I see Jeff, you're working out something, you're doing some math. You're the only person I could see. But yeah, if anyone can, like, please do this along with me. And then I don't have a calculator, so I'll need someone to tell me the answer. So this is 10 squared, so that's 100. 1 minus, so 1c over 2 squared, it's just c squared over 4 minus c squared over 4 divided by 4. So that's 100 minus 1, divided by c, not 4, divided by c squared. So that is the 2c squareds cancel out. And then we get 100 over 1 minus 1/4 is 3/4. So that's just like 75. So my time squared is 75, and the square root, or the twin, okay, the twin's time is a square root of 75. And then what is that? Could someone tell me if anyone has a calculator on them or has beat me to doing this? That's just about 8.6 hours. So while I wait for 10 hours in the line, for 10 hours that passes for me, only 8.6 hours passes for my twin moving at the speed of half the speed of light. And it gets really close. And plus, you can't really see, like, you can't really move. So if you try moving, let's say we plug in v into here. So let's say we take this equation. Is there any questions, by the way, before we move on? Oh, yeah, sorry, I skipped the big, okay, so this is 100, 1 minus 1/4, and then that would be 3/4. And then this would be 25. 25 times 3 is 75. So this is just like a typical, like, this is like a pretty simple, like, manipulation that you would do. This is just good to give you a taste of if you decide to go to study physics in college. This is, it's something. It's like, you take some variables, you move them around, you shuffle some variables around, you get new rewrite equations to make them look differently. So this was just, we just made this geometry. We just made the Pythagorean, like this whole thing, this equation that we derived relating to two quantities just came from the Pythagorean theorem in 4 dimensions. So you start with simple basic geometric concepts such as the Pythagorean theorem, and then you get, you could derive some equations which will give you some physical effects that you could calculate things with. Okay, so what if you're moving at the speed of light? What happens? Did someone tell me? Yeah, what if you plug in C for this? What if you plug in C into here? You take C and you just plug it into this equation. What do you get? You would probably die. Okay, how about very close to C? How about almost C? very, very, very close to c. Yeah, time would stop. So essentially, if you're moving insanely close to the speed of light, like 1,000,000 years could pass for someone on Earth. But for you, like it'll pretty much be nothing. So let's just say this is like 0.99. So let's say your speed is v equals 0.9999 c. Then this would be 1 minus 0.99999 c squared. Oh yeah, more than that. So I'll be like really small. So I'll pretty much be like, so like 1,000,000 years could pass by for this person. We'll just make it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whatever. 1, 2, 3. Yeah. No, it's too much. 6. 1, 2, 3, 4, 5, 6. So let's just say you're going around this speed, for instance. So 1,000,000 years could pass for someone on Earth, and then only like maybe like 1 year would pass by for you. Yeah. So the faster you go speed of light, like the more time stops for you. So are rich people trying to co-freeze themselves probably the ones that paid psychro fees? Yeah, not sure. Not sure. Oh, the concept of light years. Yeah. So light year. So that's how fast. So a light year would be so the speed of light moves 6.07 miles per hour, or 6.7 times 10 to the 8 miles per hour. And then how many hours are in a year? Does anyone know? I'll look it up. Sorry, I'm getting some messages. Hours in a year. So hours in a year. So what you would do, there is 8,760 hours in 1 year. So this would be 1 year per hour. Is that right? 7 hours in 1 year. No. This would be hours for 1 year. So then when you do this, you pretty much multiply this number by this to get light years. So 1 light year would be 6.07 times 10 to the 8 times, times 10 to the 8 times 8,760 miles per per year. Okay, so 1 light year is just this many miles. Sorry, 6.07 times 10 to the 8. So it's a lot of miles. So it's like, this is quite a bit of miles. Yeah, true. Okay, so okay, so now we'll move on. So this was how Einstein formulated, okay, this is how our space works. Our universe is actually 4 dimensions. It's not just 3-dimensional space, it's 4-dimensional space-time. And he used this to come up with a new theory of gravity, which has so far is extremely successful. So before Einstein, the theory of gravity was with Newton. So Newton said that, so in high school physics, you'll learn, well, I mean, for you, like time will be ticking normally. Sorry, I'm answering Jeff. You could basically live forever if you went around the speed of light. So for you, like on your clock, like if you're carrying a clock with you going to speed, like almost the speed of light. So your clock will still be like, if you read a book, like, like you could like, I don't know, read like 80 years worth of books going to speed of light. And then you'll like, it'll be the same. Like you're not going to feel any different. Like you're not going to live longer by going the speed of light. But what will happen is people are going close to the speed of light. But what will happen is like Earth will be far gone. Like people, like, you know, like it will be, you know, our galaxy might be destroyed. Everything we know will be completely different. Even going close to the speed of light for like a very small amount of time, like you come back and, I mean, it's very not reasonable to go that fast. It takes an insane amount of energy. But yeah, practically, like, let's just say I like go to my kitchen real quick and I go very close to the speed of light, like extremely close to the speed of light. I could come back and like, I'll be like 1,000,000 years into the future. Even just going from here to my kitchen, as long as I'm moving that speed, because time will tick so slow for me. Yeah, like 1,000,000 years would be like, actually, no, that would be, yeah. I wouldn't say that. I would say that, yeah, that would be, but okay, let's just say I go on the space and I just travel for like a very short amount of time, like close to the speed of light, and I come back. Maybe for like 1 second my time, close to the speed of light. So I go close to the speed of light for 1 second, come back millions of years in the future. Yeah, so I guess that's really interesting. If we go back to this equation, let's see how much like light normally moves. Here you go. Let's see. So it'll be really interesting is that, and I'll cover this later, but I could just do it now because people are, okay, there's people coming in. So how far does light move? So what space-time distance does light move? Okay, so we have this ds squared equals dx squared plus dy squared plus dz squared minus c squared dt squared. So let's just divide everything by t. So we just pull out a t, t squared, and then essentially what we're left with this is just vx squared plus vy squared plus vz squared equals v squared delta t v squared minus c squared equals delta s. Okay, so this is a formula that you could get. So when v equals c, we find that delta t squared c squared minus c squared equals delta s squared. And then this is 0. So actually light doesn't move any distance, which is pretty crazy. So it's like the light in my room, I guess. What I could say is that I turn off this light, and then if I turn it back on, it's not really the light that moved, but it's that I moved through time and hit the light. That's like, that's essentially how to think of this. Yeah, but that's like, well, this is getting like in the depths of, you really have to start thinking about these things, and you start noticing this stuff. But this is just like, I'm doing this just to give you like an overview of why it happened. Well, I mean, this is like, yeah, I guess this is like some subtleties, like what do you mean by traveling? It's like, to us, like relative to us, in our fixed frame, like we see like light moving at us. But then really in this, if we step back and look at things from like a 4-dimensional point of view, it's like we kind of just like run into the light. The light doesn't move at all in this 4-dimensional point of view. Sorry, this is just a cool caveat that I want to let you guys know. Okay, let's go into general relativity. I think I have about 30 more minutes. So So in school, what Newton says that light attracts, no, only things that go, okay, so gravitational waves. So things that go the speed of light, they're very special. They have like a very special place in our universe in the sense that they don't move through, their four-dimensional space-time distance is 0. Anything that moves speed of light. That's why we can't get to the speed of light. We have mass, like any, and light doesn't have mass. So pretty much things that don't have mass, if we have any mass, if you have mass, you need, and like a very rough sense, and a very technical sense. If you have mass, you're not moving, you're moving some distance through space-time. If you have no mass, you don't move through space-time. Like things that mass move kind of evolve into you. Okay, so light doesn't have mass, by the way. And that's important. I'm going to talk about this concept right now. So in Newton, Newton said that gravity is just the attraction between two massive objects given by this equation. So if I drop, this pen has mass, the earth has mass, this exact equation could tell us, and this is a constant, we plug in the mass of the earth here, mass of the earth, we plug in mass of my pen. This is just some constant, I wrote it down later, and this is how far my pen is from the earth, and then, or the center of the earth, I should say, center of the earth. And it gives you the force. So that's why anything with force moves. So without force, there's no motion. That's like Newton's law. So if something's moving, there's no forces acting on it, it'll keep moving at the same speed. But once you include forces, you include acceleration. So the force of gravity, it causes the pen's speed to increase. So the pen moves faster and faster, and that's what we call a force. When like the earth causes the pen to, the speed of the pen to change, the speed of the pen to increase. So that's a force. Okay, but so according to Newton, since light doesn't have any mass, it shouldn't feel the gravitational force. The force should be 0. But then in 1917, there was an experiment that proved this wrong. We see that like light going around the sun actually bends. So light feels gravity. And this was actually, so this experiment was done in 1917. Einstein predicted this in 1915. So his idea that space, and his idea which predicted this was that anything with mass causes space to curve. And really, when we see that this pen is falling to the earth, the orbit of the moon around the earth is orbiting the moon. We're actually saying the moon is actually moving in a straight line, but it's just the space around it that is bent. So a straight line would be, no. Oh, this is, yeah, we have quite a bit to cover. So a straight line would be just going around this, the sun. It would just be in an orbit. So it's pretty much just like curving. And then the more heavy something is, like the more dense it is, the more curved space. So if you take the mass of the sun, or the mass and the radius of the sun, curve space a little bit. If you shrink the radius of the sun, keep the same mass, but shrink the radius, it'll bend it more, shrink it more, bend it. And then if you shrink it a lot, it'll become a black hole. And actually the sun can't become a black hole because of what it's comprised of, but like other stars, maybe like stars 20 times bigger than the sun, could become a black hole. I'm not going to go into detail. I think I'm just going to skip to the black hole part. But essentially, I just want to talk about like curved space. So in flat space, like a piece of paper, if you could draw any triangle you want. The sun will be 180 degrees. But however, if you take a ball, like take a ball at home, and draw a triangle on it, if you draw like 3 right angles, so all these angles are 90 degrees, you can actually form a triangle on a ball, but the sum of the angles would be 270 degrees. So I think that's a cool fact. And this is used to tell if like space is curved. So at like large distances, we can make triangles. So if you draw like a very small triangle on a sphere, it'll still pretty much be 180, depending on how big your ball is. Like if you have a big ball and you draw a small triangle on it, it'll be 180. But then if you draw like a big triangle on a big ball, that's when you start to see its curvature come in. As curvature alters the math by altering this, the sum of the angles is 180. That's how you could tell if something's curved. If you have a flat surface, no matter how big you draw your triangle, the sum of the angles will be 180. If you have a curved surface, the bigger you draw your triangle, the more it will deviate from 180 degrees. And yeah, the Pythagorean theorem also gets modified. So our 4-dimensional space-time gets modified a little bit. Let me just show you how it gets modified for gravity, and I'll come back. So for those of you who have taken physics, high school physics, all you do is you multiply some factor of like the Newton's potential into this Pythagorean theorem formula, and that's how you curve. So the Pythagorean theorem formula that we had up here, this is for flat space only. If you want to add gravity, you just kind of like multiply some the space and the time by certain factors, and the factor just happens to be the potential energy for the gravitational field if you have taken high school physics. You could also see, by altering this this Pythagorean theorem just a little bit, you could actually get the expansion of the universe. So the universe is expanding. So that means that every galaxy, like pretty much like even my room right now is like slowly getting bigger and bigger and bigger from all directions. And then, yeah, so so this planet is slowly moving away from all the sun, like the sun and the other planets, like everything is moving away from each other. Our galaxy is expanding. The distance between all the galaxies around us is expanding. Pretty much the whole universe is expanding. So how can we model this using, how can we modify this to model this expansion? Is there any questions about the expansion? I think that's a really cool topic. I have a lot of slides that definitely not going to get to, seeing how everything expands, going into much more detail about expansions and how the 2 galaxies, like every galaxy is receding from itself. Yeah, in fact, I'll just jump to here. So if we see like, if all these dots, this is like our whole universe, all these dots are galaxies, we see that like the universe as a whole is expanding using this Pythagorean theorem, which I'm going to show you now. So sorry, let me go back. Okay, so how can we model this expansion? Yeah, any questions, by the way? That's aging, right? Maybe it would explode. What? So, oh man, I think I'm missing a lot of these. If you live long enough, you'll be bigger. That's what aging is, right? Well, yeah. So, I mean, we'd still age if the universe expanding has nothing to do with us aging. In fact, before, like even Einstein did not, like when Einstein was around 100 years ago, no one thought that the universe was expanding. This is a new thing. So in the 1980s, that's when we saw like, oh my God, the universe is expanding. So this is like, yeah, so you probably like you have grandparents that were born when like the idea of the universe expanding just was non-existent, or like no one knew that the universe was expanding. So this is a new observation. This is really cool. So I would encourage you to look this up on YouTube or something. So we could just put like, we just multiply just the space. So we only need expanding in space, like only the space expands. So we can just multiply the space direction by a factor, AT. It's usually complicated, like it's like T cubed over 2. But let's just keep it simple. AT, you will see, does the universe expand? So there's, yeah. So there, so right now the universe is finite, but it could keep expanding to infinity. So we'll see. Well, let me just, let me show you. But yeah, so essentially the universe is, right now it's finite because it started from a big bang. It went like a finite time. Like the universe is only like 13 billion years old. So it can't be infinite now, but like it's like, what is it expanding into? Like it's not expanding into space. Like that's like, these are some concepts. You think of like if bread expands, it's like, oh, it's expanding into the air around it, but this is space itself that's expanding. So there's really like, you can't picture like the universe in like some spatial region expanding. No. Okay. So let's two friends be separated by some, we call this the east direction, delta x. Let's just call it 5. It could be 5, whatever, 5 feet is 5 feet. Why not? 5 feet. So at t equals 1, a t of 1 equals 1. So this gets multiplied by 1. Since delta x is 5, this is 5 squared. This is 0. This is 0. We're not looking at the change in time, so we could say the change in time is 0. It's not like we don't want to get that in depth. So the change in time is 0. So that's ds is just 1 times 5 squared. So it's ds squared equals 25. And then their distance is 5 from each other. Okay, so let's see what their distance is at t equals 2. At t equals 2, we have a2 equals 2. So now our line element would be 2 times all of this, 2 times this, and then low battery. It's be bad. It'll be 2 times all of this, and then what happens is that when you multiply this by 2, we could plug in 5 for here. They're still only five blocks from each other. You could say blocks. That's even better. 5 blocks from each other instead of feet. Yeah, 5 blocks. So now there are 5 blocks from each other. But however, their distance, when you plug this in, you plug in 5 into here, 0, 0, 0. You get ds squared. I think I did this calculation here, but let me just do it again. I think for ds squared equals 2 times 5 squared. So this is equals 50, ds squared, and ds equals the square root of 50, which is something like 7. I don't know, this doesn't seem right. Yeah, no, 7. Yeah, 7 squared is like 49, so it's about 7. Cool. So now they're actually like their distance expanded. So what about at t equals 0? Well, at t equals 0, what happens? So at t equals 2, the distance was about 7. At t equals 1, the distance was about 5. But at t equals 0, you could plug in 5 meters from here, and you get 0. The total distance is 0. So you get a big bang. Okay, let me answer some questions. Okay, you guys are really interested in this universe expansion. Do things expand at? No, the whole universe expands at the same rate. Also, if the Earth is moving away from the sun, does that mean it will move out of the? Yeah, probably, but this expansion is really small. Like you can only see it at like galactic scales, where like things are like millions of light years apart. That's when you notice. So I think like 2 objects, like 2 galaxies, like millions of light years apart, they'll probably be moving away from each other at like 20 miles per hour. But I mean, the universe is like trillions of galaxies. There's so many galaxies, like hundreds of trillions of galaxies in the universe. So at a small scale, we don't see it expand. Like, no, like we're not, you're not going to grow in height. Yeah. But yeah, eventually, yeah, if the solar system lives forever, then eventually the Earth will go out of the sun's orbit due to expansion. So that's cool. We don't know if it has a limit or not. It depends on the geometry of the universe. What if you were standing in space in the galaxies? Would you expand? Yeah, so the distance, so pretty much, yeah, so you would expand. So we're expanding now. It's just so small. Like it's insanely small that we're expanding. So like we're getting bigger, like everything. Like top, bottom, like front, back, everything is it's just insanely small. Like it's not even worth you only see the expansion at these little expansions add up on the scale of millions of light years. But yeah, let me just jump to this. So we have to talk about black holes. Yeah, probably we'll talk about black holes, and there's like I do want to mention something about time. I think that's pretty interesting. I'll probably like wait till the last 5 minutes and pull that trigger. So it depends. So the universe could be flat, which is what we're describing. The universe could be closed like a ball, or the universe could be open, like kind of like a hyperboloid, like some like hyperbola shape. I don't know if you know Escher, the artist Escher, but Escher draws these geometries represent some like hyperbolic geometry, which kind of you could look at Poincare disk. I would say you could take a screenshot of that, but essentially this like encodes like the fact this is negatively curved. So if you draw a triangle on here, the sum of the angles will be less than 180. If you draw, and this is the universe I'm talking about, like if you draw the sum of the angles will be greater than 180. So what happens if the universe is like a ball, if it's like shaped like a ball, like if it's circular, the universe will reach a maximum point of expansion, shrink, and then recollapse. But if the universe is negatively curved or flat, the universe will just keep on expanding forever. So if you're looking for faith of the universe, yeah, things will just be so like spread out that nothing will interact with each other. Yes, the universe will die either way, or it will. I think the only way that the universe won't like die is with this closed universe, because what happens, it keeps like shrinking, expanding, so it keeps like it just goes on forever and ever. Any questions about this? Yeah, but these are like, yeah, trillions and trillions of years. Like it's okay. Like we're fine. That may even more. I'm not sure when things would recollapse. Oh, it's morbid that the universe will end. Yeah. Well, maybe there's multiple universes. Like there could be multiple universes. So that's what some like speculative theories are about. And I want to talk about some speculative theories like string theory. It predicts like multiple universes. So maybe we could jump to another universe. So it doesn't really have to be so morbid. Who knows? Okay. So who knows? Yeah, I guess we can't really know how the universe began. But anyway, so please watch the YouTube videos. It'll explain to you. It's a simple derivation for a black hole, but I just I don't think it's really nice. If you've been following the mathematics, you'll see that using this equation, if you plug in R equals GMC, which that means so in words, if the mass of the Earth, if we have some mass, if any massive object ends up fitting in a ball of radius r, given by r is g, which is the Newton's constant, and that is 6.6 times 10 to 11. So this is so there's so like I said, if an object gets small enough, it'll turn into a black hole. So the exact radius this has to be is given by this equation. R equals g, the mass of the object, over the speed of light squared. So just for perspective, let's say the Earth could go into a black hole. How small does it have to be? Well, the radius has to be less than this given radius over here. So the mass is 5.797 times 10 to 24. So we could put that in here, here, and then plug all these things in. And what we find is that The event horizon that the Earth must be a black hole is about 0.4 centimeters. So that's like a fourth of a dime. And then the radius of the Earth is actually like almost 4,000 miles. So we have some, the Earth being about 4,000 miles, have to shrink into the size 1/4 of a dime. So I think that's right. Yeah. Half a centimeter. Yeah, maybe a dime. Cool. Yeah, so that's the black hole. Does anyone have any questions about black hole? So let's just say I picked Winnie the Pooh. Let's just say you have any, let's say Winnie the Pooh has mass of 75 kilograms, which is just like a normal human. The event horizon would be 5.5 times 10 to the minus 26 centimeters. Yes. Yep. So you'll see why. So how could a black hole die? That's where we'll get to next. But what happens at the black hole is, okay, let me actually go back to this equation, which I just briefly motivated. So we're curving space with the geometry. So if we plug in R, so we have this equation and we plug R equals GM over C squared, which is done over here. So let me see this. So what happens is this term, when we plug in R for here, what happens is this whole thing becomes 1. Maybe I could show this to you. So 1 minus GM C squared, GM C squared. We just divide it by GM C squared. This becomes 1, and 1 minus 1 is 0. So essentially at this event horizon, where it forms a black hole, this would be 0, and this would be 0. So essentially time stops again when you're at a black hole. So somebody who is falling into a black hole, or the time stops for someone looking for someone, time doesn't stop for someone going to a black hole. If you're falling into a black hole and you somehow survive, you're going to the center of the black hole you're going through. But then if someone's just chilling on the outside of the black hole watching someone go in, that person will never see it, because going to a black hole is like going the speed of light, like essentially like approaching that horizon in many respects. I see something that said, yep, there's a huge black hole in the center of the Milky Way. That's true. Yeah, dark matter is just outside of our galaxy. Dark matter is around everything in our galaxy. We can't really see dark matter. We could detect it with gravity, so we know it's there because it has a gravitational effect, but we can't see it. We don't really know anything about dark matter. We're trying to figure out ways to detect dark matter now, but that's a particle that we just don't know of. Maybe it might be something different, I don't know. But right now, everyone thinks it's just a particle. And we don't really know its properties because we don't have it in a lab, but like it affects gravity. So we think that like dark matter is like just around, it hangs out around galaxies. And there's like some good frameworks for that too. So I did mention, as advertised, about wormholes. So what happens is that wormholes, if you could bend space in a certain way, such that like just like this piece of paper, instead of space bending to make a black hole, which like pretty much like space gets like kind of pulled down the center, it could bend and create like a wormhole in which like 2 regions of space are connected to each other. That's the wormhole. That's pretty cool. We could use it for space travel in the future. This is actually like way after your time. This is hundreds and hundreds and hundreds of years into the future. we'll be able to create wormholes and use them for space travel. Probably that's like theoretically things should work out smoothly with using wormholes for space travel. And there's also like warp drives too. I didn't get a chance to talk about that, but I'll make a video where in some region you could go faster than the speed of light. But I didn't have enough time to explain that. Okay, so black holes do not live forever, they radiate. So what happens is they get smaller and smaller. They radiate light, electrons, protons. It's like a furnace, like you see some black body spectrum. The temperature is actually the inverse proportional to the mass. So the smaller the black hole is, the hotter it is. And then, so smaller black holes radiate much more than larger black holes. No. So they shoot out really light particles like electrons, and they don't radiate a lot. Like they just radiate like very light things, light particles, and they just like expel them like really fast out into the. In fact, sometimes I think I'm not 100% sure on this, but I haven't studied this in detail, but pretty much like in every black hole, like there could be a wormhole that like actually like deposits the radiation somewhere like really far away from the event horizon of the black hole. So what happens is like there's like a wormhole just spitting out things in the black hole, causing the black hole to shrink. Yeah, just I'm not too I haven't studied that too well. Understand that process completely, but it seems pretty. That's like the way to go. That's like the best way to go. The best way to describe this radiation is with the wormhole, and it shoots like what's inside of the black hole goes through the wormhole and then gets deposited somewhere far away from the black hole, so it can't suck it in. Yeah, exactly. So the Hawking, yeah. So this is Stephen Hawking. He was in a wheelchair. So I guess like, yeah, I think you should look this up, like Hawking radiation. There's great videos online. But yeah, exactly. So it can only make things smaller, but then the smaller it gets, the hotter it is. So the faster it radiates. So big black holes radiate slowly, small black holes radiate fastly and lose more mass quickly. So it's like an exponential mass loss. 5 minutes. Okay, we got this. Any pressing questions, please put them in the chat. So the thing about it is like, so Einstein's theory actually breaks down when you're about, so I guess the question is, can a black hole radiate to nothing? So black holes are radiating particles, so it gets smaller and smaller and smaller. But the problem is that Einstein's theory breaks down at around 10 to the minus 35 meters. So it's really small, like it's a super small where Einstein's theory breaks down. But so we have to raise the black hole gets below that. Like, could it radiate still? Like, what happens? Well, we don't know, but we need new theories for that. One of them is string theory, where essentially particles are just strings that are around the size that gravity breaks down, classical gravity breaks down, general relativity, so about 10 to the minus 35 meters. The more they vibrate, the more massive they are. So like particles with zero mass, like light, they just have, so like picture like a string, like literally just like a guitar string, or like, you know, one of these this headset string. You know how like you could pluck it, like the lowest frequency is a massless particle, so that's light, and then the higher the frequencies, the higher the mass. So what happens is, since like the string is the size that the radius, like general relativity breaks down, when black holes reach this kind of Planck length size, which we don't know what happens to it, string theory predicts that it'll just like convert into like some like really like highly vibrating string. So the black hole just turns into like a really like vibrating string of that, a super massive particle. of that, and then the particle will decay more. That's not really that interesting. That's not like super. Okay, what string theory is like? It has like a lot of interesting predictions, such as there being like 11 dimensions, like meaning like 11 space-time dimensions that are like really small. Something else that's pretty interesting is that like there's actually just no space. Space just literally does not exist below 10 to the minus 35. So 10 to the minus, I could send them. I'll send them. Don't worry. So space just does not exist at all around 10 to 35 meters. So you could just think of like it kind of being like a grid almost. And then 10 to the minus 35 meters. And then, you know, things can't exist. So like, if you have like, okay, like the area of like this region of space, you could just calculate the area by how many grid lines pass through it. And like, let's just say you calculate this area of space and no grid lines pass through it, then this has like 0 area. So that's pretty interesting. But okay, so right now the smallest area could only be 10 to the minus 35. Well, actually time, what happens is that like what is time? Like time is just the ticking of the clock, but you could really just say it's change. So if nothing changes, there's no time. That's essentially what happens. So what happens is that since light can only move at a finite speed, it could, and nothing could happen while it travels this distance. We say that time just like there can't be any change. So the fastest that something could change is the speed of light moving this distance, because that's the fastest thing. So that so because of that, it takes a finite amount of time for light to travel this distance. So below that time, we could say that time just doesn't exist. Okay, we're cashed out of time. So thank you.